Okay, in this video we are going to begin our final exam material. So to start off in this video, we're going to do three sections. We're going to do sections 3.1, 3.2, and 3.3. It's a little bit longer of a video, so just kind of be prepared for that as you watch it. In section 3.1, we are going to talk about the difference between what a relation, and then we're going to get into our big topic, what is a function in terms of how we're going to use it in this class. So a couple definitions here. I'm going to kind of go through these a little bit quickly. If you need to pause the video to write them down, that's fine. So what is a relation? So a relation is any set of ordered pairs. So when you're plotting points, all those ordered pairs that you have are considered a relation. We can define the domain as the set of all first components of the ordered pairs, which is your x values, and we can define the set of all second components of ordered pairs, or the y values, as the range. Domain and range is a big thing we're going to talk about in this video. So then what is a function? So we got a relation down, so what's a function? A function is a correspondence from the domain to the range such that each element in the domain corresponds to exactly one element of the range. Every function is a relation, but not every relation is a function. So essentially what a function says is that for every x value or every number in the domain, you can only have one number in the range. So let's say that your x value is 2. You can't have the ordered pair, let's say 2, 1, and 2, 4. Same x value, but they have different y values. That's not possible in a function. It's still a relation, but that would be an example of where it is not considered a function in this case. So to kind of show you some basic example here, what I've done is I've made up some relations and we're going to talk about them. So first thing is determine whether each relation is a function, and then give the domain and the range for each relation. So we're going to end up doing all three of these. While it asks you the first question, I actually usually answer that second. So I'm going to move to the second statement here and say give the domain and range of each relation. So I'm going to label domain as my D value, and then range we'll just call R. So starting with the domain, if you look at all 5 of those points, negative 1, 5, 0, 2, 1, 5, 2, 3, and 1, 7, you need to write down the x values because every different x value is in the domain. So if I just go from left to right, we have x values of negative 1, 0, 1, 2, and then you notice the 1 repeats. If the number repeats, you do not have to write it again. So I'm just going to close off my brace, and that is my domain. The range is the set of all y values. So now look at the y values of your point. You've got 5, 2, 5 again, so don't worry about that one. Then you have a 3 and a 7. So that would be your range in this case. And now the question is this a function? So remember, if it's a function, if there is a double up of x values, they have to have the same y value. Unfortunately, if you look, you have an x value of 1 here and an x value of 1 on the last point. They do not have the same x value, and that's not a good thing. So while this is a relation, the question is it a function? Absolutely not. This is not a function by definition. So let's look at a second one. What about the points negative 1, 5, 0, 2, 1, 5, 2, 3, and 3, 7? So made one slight change. I changed the last point's x value to show you how it can be different. So when you do the domain here, you're going to have negative 1, 0, 1, 2, and now 3. So that would be your domain here. Versus your range, I didn't change any of the y values, so it's going to be the exact same thing here. It's going to be 5, 2, 3, 7. The difference this time is that since none of the x values double up, so every single x value is different, automatically without doing anything else, I know that yes, this is a function because there's no way the same x value has different y values in this case. All right, so now let's look at some functions. One of the big things you got to be able to do in this chapter is evaluating functions. So let's do a couple examples of those. Number 3, if I define the function f of x as being 3x minus 4, can you evaluate each of these and simplify your answer where necessary? So when you see something like this, we've done things like this, just never defined in this way. When you're asked to do something like f of negative 3, all you're being asked to do here is take that -3, plug it into your function, and simplify it. So this would be 3 times -3 minus 4, which is -9 minus 4, which is -13. That's all it takes to evaluate a function at a number. And you can do that for any number or any polynomial that you're given. So what about f of 1/2? So if I plug 1/2 into the same spot, so it would be, oops, I didn't mean to write it that way, but you can kind of see what I was going for. Let me just erase that. We are going to take 3, multiply it by 1/2, subtract 4. So that would end up being 3 over 2 minus 4. If you find common denominators, that would be 3 over 2 minus 8 over 2, because 4 is the same thing as 8 over 2. Then you can subtract them to give yourself an answer of -5 over 2. Now where you got to be careful at is what happens if it's not a number, but instead it's an actual polynomial. Well, it's no different. You're going to take this x minus 5 here and plug it in where you see an x. So that would be 3 times x minus 5 minus a 4. Distribute the 3 through. So that is 3x minus 15 minus 4. And then combine your like terms, which are the two numbers here, and you should get 3x minus 19. And that's the basic idea of evaluating a function. Now, they can get more difficult, and I think the next one we're going to see is a little bit more challenging, but that's all you're being asked to do when I say plug a number into a function. All right, so let's look at this one. What if I define f of x as being x squared plus 1, and I want you to find f of 2, f of -2, and f of x minus 1? So for f of 2, once again, you're just plugging this number into your function. So that would be 2 squared plus 1, which is going to be 4 plus 1, which is 5. It's no different when you plug in -2. Now, something you'll see me do a lot in this chapter is that when I plug negative numbers in, I usually put them in parentheses so I don't mess up. So this would be -2 squared plus 1, which is, once again, 4 plus 1, and you get 5. So you get the exact same number whether you plug -2 or 2 in. Now, what if you plug x minus 1? So I'm going to replace that x with an x minus 1, square it, and then add 1 to that. You will have to rewrite this because you're going to have to FOIL it as x minus 1 times x minus 1 plus 1. FOIL those first two together. So first, outer, inner, last. That's going to give you x squared minus x plus 1. And then don't forget the extra plus 1 on the end. Combine your like terms. Looks like you're going to have an x squared. Combine both the x's and you'll have a minus 2x. And then combine both the ones and you get a plus 2. So that's how you can evaluate this function at x minus 1. Very good. So make sure you know how to plug numbers into functions as we go through this chapter. All right, so a special formula that you might see from time to time is called the difference quotient. So make sure you jot this formula down in your notes for when you get to your homework. So the difference quotient is defined as the following fraction. It is f of x plus h minus f of x divided by h. So what's going to end up happening here is you're going to plug, based on the function you're given, you're going to plug in what you know, and then it's going to take a lot of simplifying to get down to a simplified answer. So let's look at this difference quotient here. When it says f of x plus h, that means that you are going to replace the x in the original function with an x plus h. So to start that off, it would be 2 times x plus h minus 5. So I just took the original function and changed the x. Then you have to subtract f of x. So in parentheses, I'm going to subtract the original function here. So minus 2x minus 5. And then you have to divide all of that by just a single h. And your job now here and on your homework will be to simplify this down as far as you can. So in the numerator, I see that I can multiply the 2 through on the first parentheses, which will give me 2x plus 2h. Bring down the minus 5. Then distribute that negative to both terms. So minus 2x plus 5, all of that divided by h. And at this point, you'll start seeing some things cancel. You notice that your 2x's cancel, and actually your 5's cancel as well. And usually you're left with something very nice. In this case, it's just a 2h divided by h, and there you can see that h divided by h goes away. So in the end, the difference quotient of 2x minus 5 is just going to be 2. Now, once again, I'm going to show you a little bit more difficult one on the next slide, but that is the basic idea of when you're asked to find the difference quotient. So let me show you that more difficult one. So, can you find the difference quotient of 2x squared minus 3x? So kind of working this the exact same way. If I'm using this difference quotient up here, the first thing I'm going to do is I'm going to turn both of these x's into x plus h's. So that's going to be 2 times x plus h squared minus 3 times x plus h. Then I'm going to subtract and open a parenthesis. So I'm going to subtract the f of x, or the original function, which is 2x squared minus 3x. And then I'm going to divide all of this by h. Now the second and third parentheses, those are not too hard to deal with. That's just distribution, but you will have to do a little bit more work on that first one. So let's rewrite some things out. This would be the same thing as 2 times, and instead of x plus h squared, I'm going to rewrite that as x plus h times x plus h. Now, like I said, the second and third parts, that's just distributing. So I'm going to distribute the negative 3 through. So that's minus 3x minus 3h. And then I'm going to multiply this negative through and make it minus 2x squared plus 3x, all divided by h. Now, while we can't see all of the canceling right now, cancel where you can and take off some terms you have to keep writing. I noticed right away that these 3x's in the top go ahead and cancel. Let's just deal with that and not have to worry about it as we go through. So coming down, I'm going to leave the 2 alone, and then inside parentheses, I'm going to FOIL the x plus h times x plus h. So if I do my FOIL technique there, it will be x squared plus xh plus xh plus h squared. So that's the FOIL. Everything else stays the same. You still have a minus 3h, a minus 2x squared, all of this divided by h. Now I'm going to distribute that 2 to all of those terms. So that's going to end up being 2x squared plus 2xh plus 2xh plus 2h squared minus 3h minus 2x squared. All of that divided by h. I notice something else cancels. Maybe you see it as well. 2x squared, excuse me, minus 2x squared cancels. And while the next one doesn't cancel, there is something that combines. You can put together these 2xh's into one term. So that's going to end up being 4xh plus 2h squared minus 3h divided by h. Notice that everything shares an h in common. Now there's more terms than we had last time, but now you can go through and you can cancel an h out of everything. That should always be your last step in these difference quotients. So while the h on the bottom cancels, I can get rid of the h in the first term, one of the h's in the middle term, so there's still an h there, and that h goes away in the last term. So what's left over? You have a 4x, a plus 2h, and a minus 3. This is the simplified difference quotient of 2x squared minus 3x. And that's probably as hard as one I will give you. So if you can do one of that difficulty, you should be able to do any of the ones that I ask you to do on your homework. So very good. All right, so how do you so we talked about how to determine a function if you're given a relation. How do you determine a function if you're just given the graph of it? So there's a nice simple test called the vertical line test. It says that if any vertical line intersects a graph in more than one point, then the graph is not a function. So I went into the textbook and I pulled these 3 graphs out of the book, and I want you to say, can you identify which of these is a function and which of these is not? So here's all you have to do. If you look at the very first graph, you have kind of this little loop-de-loop with a straight line. All you're asking yourself is that if I draw a vertical line anywhere, and I'm going to draw a bunch of them on here just to show you, and I'll even draw one really, really close to the point. Every single one of those vertical lines only crosses the graph once, and you can do that anywhere. If that is true, if it only crosses once everywhere, your answer is yes. This is a function. Number 8 is very similar. You can drop as many vertical lines as you want to, so I'll drop a few of them here and there. And even the one you're not sure about, if you drop one right here on the open circle and the closed circle, since the first dot is open, technically it does not exist there. So when you go and check all of your lines, all of these vertical lines technically only cross once. So when the question is this a function? Yes, this is definitely a function. Now number 9 is not that same thing. Right away, I can tell, and I only got to draw one line to show you. I have just drawn a vertical line that crosses the graph more than once. That's fine. There's ways to write that equation, and you can learn that in other classes in different ways. But for this class, if it crosses more than once, it's not something we're going to deal with a lot of. So no, that is not a function that we can deal with. Very good. So that is the vertical line test. All right, so types of functions. Once again, I'm going to kind of run through this kind of quickly, so if you need to pause the video, that's fine. We can classify functions in 3 different ways, and that's on the left-hand side here. We can either call a function a polynomial function, a rational function, or what we call a root function. So what are the differences in all of these? So first off, let's talk about polynomial functions. A polynomial function is just a simple function written in the form of all these a's are just constants, and then you have a bunch of x's involved. Essentially, you don't see any fractions, you don't see any radicals, so if it's just a nice simple one-line term, we call that a polynomial function. Now the benefit of polynomial functions is this last part. You don't have to do any work. The domain of a polynomial function is always negative infinity to positive infinity. That means every single x value works in that function. All right, rational functions is any function that can be written in the form of g of x over h of x, where g and h are both polynomial functions, as long as h of x cannot be 0. And that part is important, this part right here, because that leads us to the idea of the domain. The domain is the set of all numbers, except whatever makes the bottom 0 is not part of your answer, because you cannot have a 0 on the bottom. All right, then you have root functions. So root functions, you can also call these radical functions, but our book calls them root. Essentially, you're going to have some kind of radical in your problem. You're going to have an nth root of g of x, and then what's important here is not so much what's on the inside yet, is what is true about the root. Your root is going to be any number greater than or equal to 2, and depending on what kind of number it is going to dictate how we do the next part. So 2 parts here. If the root is even, then the domain is the solution of the inequality g of x is greater than or equal to 0. Because if it's an even root, the inside cannot be negative, otherwise you get those complex numbers we talked about, and we're trying to avoid those at all costs right now. The better one is if n is odd, then the domain is the set of all real numbers for which g of x is defined. So that's going to be the nice one. Most of the time, if n is odd, you can refer back to one of these 2 rules, and either you'll set the bottom of something equal to 0, or the domain will be all real numbers. But we're going to see what happens in the next few problems. All right, so here to kind of show you the basics is here's one of each type. What I want you to do is be able to classify the following functions as either polynomial, radical, or irrational, or root, and then find their domains. On number 10, we have f of x equals 6x to the fourth plus x cubed minus 2x squared plus x minus 5. Right away, this is just a bunch of x terms listed in one line. You don't see any fractions, you don't see any roots, so I know right away that this is a polynomial function, and that's their favorite kind to work with because they're going to be easy to work with going forward. And not only that, we know right away that their domain based on our chart has to be negative infinity to positive infinity. Every single number in the domain exists. Number 11 says f of x is 8 minus x over x squared. Well, I see the fraction, and there's an x in the top of the fraction, and there's an x in the bottom of the fraction. So that means this is case number 2. This is an example of a rational function. So when you have fractions involved, we call those rational functions. Now the domain's a little bit different because there is a restriction. The bottom of a fraction cannot be 0. So kind of doing a little bit of work over here. I know that x squared cannot equal 0. So if you take the square root of both sides, that means that x cannot equal 0. So you have to write an interval, kind of like the first one, that includes every number except for 0. Well, that means you are allowed to start at negative infinity. You have to stop at 0, kind of like we did on the number lines, and close your parentheses, union from 0 to infinity. This is the way you write your interval to include every number except for your restrictions. Now, if you had more than one restriction, you could do this multiple times, but our only restriction is x can't be 0. And finally, number 12, f of x equals the square root of 4 minus x. Well, right away, I see that there's a radical involved, so this is what we call a root function. Now, since the root is understood to be 2 here, and that is an even number, if you go back to your rules for the domain, it says that you have to take the inside of your radical and solve the inequality for where that is greater than or equal to 0. So if I move the 4 over to the right-hand side, that would be negative x is greater than or equal to negative 4. And then if you divide both sides, I'm going to squeeze this in here. If you divide both sides by negative 1, remember back in our rules, if you divide a number by a negative in an inequality, you have to flip over the inequality, and we can say that x is less than or equal to 4. Well, if x is less than or equal to 4, that means the smallest number possible would be negative infinity, and the largest number possible would be 4, and we would put a bracket on the 4 because of the equal sign. This is the domain of number 12. So that's kind of that is the end of our first section in this video. So that ends 3.1. That kind of showed us the basics of what functions are and showed you a couple of things about what functions can do that we're going to need in the next few sections. So let's start with the next section, section 3.2. Properties of a function's graph. Now, a few of these things we may have already talked about in more basic terms, but we're going to define them a little bit different way in this section. So case in point, here's something we've already talked about, but I want to kind of go over it again because you just had a midterm on it, and it's nice to go ahead and review this for your final exam material. So intercepts are the points where a graph crosses an axis, whether it be the x-axis or the y-axis. To find the x-intercept or intercepts, because there could be more than one, you're going to let y equal 0 and you're going to solve for x. Another word you're going to see happen here is that sometimes they call x-intercepts the zeros of a function. So if you see that terminology on any of your assignments, just know that it's talking about x-intercepts. To find the y-intercept, because there can only be one of them based on the vertical line test, you're going to let x equals 0 and you're going to solve for y. And then we can write those in in ordered pair notation, which we're going to do as well. But kind of a nice little review here. Let's go over what x and y intercepts are on a couple examples. So here we go. Given these two functions, I want you to find the x and the y intercepts of each function. Now, one thing to note here is that you're not going to see a y anywhere on here. That's because if you remember, I talked about, I think in a previous section, we can say that y and f of x are the same thing. So a function of x and y are the same. So keep that in mind when you got to plug numbers in. Our first one is f of x equals 2x minus 3. I always start with the x-intercepts. That's just my preference, but it doesn't really matter which one you do first. So remember, for x-intercept, you need to let y equal 0, or in this case, you have to let f of x be 0. That means that we will have 0 equals 2x minus 3. If I move the 3 over to the left-hand side, that means 3 would equal 2x. And then if you divide both sides by 2, you can say that x is equal to 3/2. Now, if you want to write this in ordered pair notation, your x value would be 3/2, and we know that y is 0. That is the point where it crosses the x-axis. You can also do y-intercept. So the y-intercept is defined as x equals 0. So that means I can say that f of x, or y, whatever you want to call it, is equal to 2 times 0 minus 3. 2 times 0 just goes away, so we can say that f of x is equal to negative 3. And to write that as an ordered pair, x is 0 because we plugged that in, and we found our y value to be negative 3. So in this example, we found one x-intercept and we found one y-intercept. Let me show you an example where there actually can sometimes be more than one x-intercept. Number 2, f of x is equal to x squared minus x minus 6. So going through the same process, if I want to find my x-intercept just like I did above, let y be 0. So I can say that 0 is equal to x squared minus x minus 6. Now, when you have a quadratic, you can't just start moving things around. You will have to go back and remember your factoring techniques. So we're going to factor that quadratic, and it should factor into x minus 3 times x plus 2. Set both of those equal to 0. On the first one, you should get x equals 3. On the second one, you should get x equals negative 2. And you can convert both of those into ordered pairs, remember, because y is 0, and the 2 points where this graph crosses the x-axis would be 3, 0 and negative 2, 0. So this graph crosses twice across the x-axis. Now, y-intercept, you can only have one of these based on the vertical line test. So just like above, I'm going to let x be 0. And just to show you, if you want to use f of x again, you can, or if you want to turn it into y, that's fine as well. Either way, you should end up getting on the right-hand side a 0 squared minus 0 minus 6. And the only thing left over there is going to be that negative 6. And since we know that x is 0, we can write our y-intercept as being the point 0, negative 6. So just kind of a nice little review there. We've done those before, but that is once again a reminder of how you find x and y intercepts, but now just in function form instead. All right, we talked about domain and range in the previous section a few minutes ago, so now let's actually apply this to a graph. So given these two graphs, can you find the interval of the domain and the range of each function? So let's start with this first graph on the left, the one that starts at negative 5, 4 and ends at the point 3, 1. Let's start with domain because that's going to be a lot more popular, and we did a little bit more of this in the last section. The domain is the set of all x values. So when you're looking, you're focusing on the x-axis. So since the x-axis runs left and right, you ask yourself, what's the furthest left that this graph goes? Well, that would be your first point. And since we only care about the x value, that's going to be -5, which I will use a bracket on because there is a closed circle there. And then if you look to the right, because x-axis runs left and right, the furthest right point would be the point 3,1, which has an x value of 3. It's also a closed circle, so I'll use a bracket. That means the domain of this function is from -5 to 3. Now just to change colors up, because I'm going to do the same thing on both graphs, the range is your y values. Since the y-axis runs vertical, the first thing you have to do is find the lowest y value, which means that's going to be the lowest point on the graph. That's going to actually be at the point -1, 0. Since it has a y value of 0, that's going to be the first one. I'm going to also use a bracket because it is a closed circle. Then for the y-axis, you look for the highest point. Now the highest point actually also ends up being the furthest left, and that's fine. Some of these points will double up, but I'm not going to use the -5 this time. I need to use the 4 for the range. So I'll use the 4 with a bracket because of the closed circle. So the range of that first graph is from 0 to 4. Doing the same thing on the second graph, so let me go back to purple. You have a graph that starts at the open circle, and that's important, of -4, -3, and goes all the way to we don't know. But we do see that there is a vertical line here that we are not allowed to cross. This is called an asymptote. We're not going to do a whole lot with this, but just know that your graph cannot cross this. It can get really close, just not cross it. So the domain, look left and right. The furthest left this graph goes is the first point, -4, -3. So if I use the x value of -4, but I have to use a parentheses because it is an open circle. Now here's where it's tricky. Since I can't box in the furthest right, what I do know is that this graph, as we go up, it is slowly but surely getting closer and closer to this asymptote here. Now, since it never actually touches the asymptote, but I know that it gets really, really close, I can actually use that 5 as my bigger x value, but I can't include it because it is an asymptote. So my domain is from -4 to 5. All right, so what about the range? The range, we're going to look for the lowest and the highest point. Now your lowest point actually also ends up being the left point, just a coincidence there. But this time though, I'm going to use the -3 because it's the y value with a parentheses again. And then you also can't find the highest point. So using that same purple arrow, I'll put the red arrow on here as well. Since this graph is going up forever, what do you think the highest y value would be? Well, it would actually be infinity. Because since it's going to go up forever and there is no asymptote to stop it, it goes all the way up to positive infinity. And since infinity, we talked about back in chapter 1, is not a real number, therefore we have to use a parentheses there. So very good. All right, so now we're looking at doing the idea of increasing and decreasing, so, and then constant. So if you look at these intervals down here, and I just use kind of the green to break it up a little bit. So you have 4 spots. You have A to B, B to C, and C to D. So if I go from left to right, that may not be the same order as it is above, but it's okay, we'll go through them. If you look between the points A to B, you see that your graph is going in a downward direction. So anytime your graph is going downward from left to right, we call that decreasing. If in the middle, it's not going up or down. So this little green spot right here, it is going perfectly flat from left to right. So that's between B and C. We call that an interval of constant. And then finally, if you look at the increasing, you see that from C to D, this graph is going in an upward direction, so we will call that increasing. So if the graph is going down, we call it decreasing. If it's flat, we call it constant. If it's going upward, we call that increasing. That's a little bit easier, like I said, a little bit easier to see with a picture versus maybe just using definitions. So here's an example. I've given you two graphs here, and we're going to do each one. On both graphs, I want you to tell me the intervals of increasing and decreasing, and also constant. Now, if you go back and look at the last slide, you saw that none of those intervals had brackets, because in the increasing and decreasing world, everything is parentheses, so keep that in mind. So number 5, let's just start with all the intervals of increasing. So where is this graph going up? And I'll do this in purple. Well, from the beginning all the way up until you get to the first point, this graph is going in an upward direction. So that means that it starts at negative infinity. And if you also go back and look at the previous slide, increasing, decreasing, and constant is all about the x-axis. So at this first point, which is -4, that is where I stop increasing. So I'll stop that interval at -4. There's also a second interval, and that's the kind of the third piece of the puzzle here. On the second, at the end of it, we are increasing from that second point up till the third point. So since there is a gap, you have to go back and use your union symbols. This point has an x value of 2. The last point has an x value of 5. So we are increasing from negative infinity to -4, union 2 to 5. All right, and then in red, I'm going to do my interval of decreasing. So this graph is only decreasing in the middle spot. So if you look at your x values, that's going to start at -4 at the first point, and then it stops decreasing at an x value of 2. So we are decreasing from -4 to 2. There is no interval where it's flat, so therefore I'm just going to leave the constant off. There is no interval of constant on that number 5 graph. All right, so moving over to number 6, let's see how different this is. I'm going to once again start with my intervals of increasing. So looking at that graph on number 6, can you tell where it is going up? Well, the first one I see is from that first point to that second point. So that first point has an x value of -3. The second one has an x value of 0. So we are increasing from -3 to 0. That's the only spot of this graph that you are actually going in an upward direction. So increasing is done. Going back to red, let's do our intervals of decreasing. So I can see that we are decreasing on the very first spot. So since there's an arrow on the end, we're going to assume that that means we're starting at negative infinity. And then you stop at the x value of -3. But since you have a second interval, so at the very end of this graph, you are decreasing again, you're going to have to put a union symbol. It starts at an x value of 4 and then stops at an x value of infinity. Because of the arrow on the end, we don't have a finite spot, so we stop it at infinity. But we also have an interval of constant this time. So for the interval of constant, you see right here in the middle, the graph is flat. So if you use those two x values, that will be between 0 and 4. So in this second example, you have an intervals of increasing, you have intervals of decreasing, and you also have intervals of constant. All right, so one last little property here to look at, the idea of relative max and relative min. So let's go through both of these, and then I'll kind of use the graphs to help us out. A function value f of c is considered a relative maximum of f if the interval changes from increasing to decreasing at a point c. So right there, the easiest way to define this, you will have a relative maximum if your function changes from increasing to decreasing. Now that's not increasing to constant. It's not decreasing to increasing. That's the next one. If you go from increasing to decreasing, that point is a relative max where it changes. And then just vice versa with that, your function will have what we call a relative minimum if the interval changes from decreasing to increasing. Now, once again, that is not decreasing to constant. It's got to be from decreasing to increasing for it to be a relative minimum. So as you can see on the two graphs next to each one, on that first graph, your graph is going up and then back down. So that point that they're labeling is a relative max versus the second graph down on B, you're going downward or decreasing and then up to increasing. So that point is considered a relative minimum. So here's the big one. A lot of parts here. Use the graph over in that up there in the yellow, it's a lot of stuff, to find all 10 of the following things. And that way we can kind of go through each one together. And this is kind of a recap of everything we've learned so far. So part A, find the domain. Remember, the domain is your x values. So if you look for the furthest left this graph goes, that's going to be this first point, which has an x value of -8 that I'm going to use a parentheses on because it's open circle. The furthest to the right this graph goes is the point 90, which has an x value of 9, but I have to use a bracket because it is included. It is a closed circle. So that's my domain. Your range is your y values, so you have to find the lowest point. So it looks like the lowest point is the point right there, -2, -5. So if I use the y value, it would be -5 with a bracket. Then if I find the highest point, that's going to be the -6, 3. So I have to use the y value of 3 and also another bracket because they both are closed circles. So good. Remember, you can find domain and range from any graph that you're given. All right, so can you find the intervals of increasing, decreasing, excuse me, and constant? So I'm going to try my best to squeeze some of this stuff in here, but we'll kind of write a little smaller. So starting with increasing. So if I go from left to right, that very first interval that starts at -8 and then stops at -6, that is increasing. Then you keep going, and then down here at the bottom, union, at -2, you start to increase again all the way until you get to the x value of 1. So -2 to 1 is increasing. Then one more, you start again at the x value of 4, so union 4, and you stop, it looks like, at your x value of 7. So there is your interval of increasing. Then you get to your intervals of decreasing, so I'll put a little slash here. Interval of decreasing. So where are you going downward? You start to decrease here, it looks like at the x value of -6, and you stop decreasing at the x value of -2, so that's the first interval. Then you go all the way until the very end. The last little segment is also decreasing, so I can put union from 7 to 9. And that is your only two intervals of decreasing. And even less than that, you also have the idea of constant. So I'll put this right below. So the idea of constant. Can you find the straight line? Well, you only have a straight or a flat line, I guess I should say better, between the x value of 1 and the x value of 4. So that is all of your intervals of increasing, where you have 3 of them, decreasing where you have 2, and constant, there is only one interval of constant here. All right, number 9, part D says find all the relative minimums and location. So can we label the points of where relative minimum occur? Remember the definition of relative minimum. Where does it change from from decreasing to increasing? So where is it going down and then back up? Well, if you look, there's only one spot, and it's actually at the lowest spot. That is the only spot it changes from decreasing to increasing. So the only point of relative minimum would be at -2, -5, and that's it. Now, your relative maximum is the opposite. Where is it going up and then back down? So there's actually 2 spots. There is the highest spot where you go from increasing to decreasing, and also another one towards the end. So you have a relative maximum at the point -6, 3 and at 7, 2. So you have two different relative maximums on this graph. Part F, it says find all of the real zeros. So remember that means x-intercepts. So write down every point that crosses the x-axis. And I'm just going to go from left to right. So that all the points are labeled. You have an x-intercept at -15/2, 0. You have another one at -4, 0. You have a third one at 5, 0. And then at the very end, you have your last one at 9, 0. So this graph crosses or touches the x-axis 4 different times. All right, part G says what is the y-intercept? So they should only have one of these. It only crosses the y-axis once, and you can find that at the point 0, -3. All right, part H. What values of x is f of x less than or equal to 0? So this is asking me, where is y less than or equal to 0? So you have to find all the spots where the graph is below the x-axis. So that means you have a negative y value. So this is new, so I'm actually going to box these in. So if you look, this little first interval here is below the x-axis. So that is an interval I would need to use. And it says what values of x? So you're using the x values. It would be from -8 to -15/2, and I'm going to use the bracket on the equals because it has the equals on the inequality. Then you have all of this is a big interval here. All of this middle part is below or equal to the x-axis. So that would be union. It would pick up at -4 and it would stop at x equals 5. And then here's the tricky one. Technically at the very end, that last point is touching the x-axis, so you have to include it. So I'm going to do a union symbol, but since it's just one point, I put it in a little bit different notation. You put 1 point, oops, it's supposed to be braces. You put the 1 point in braces. So that number 9, I'll just put in braces at the very end. Part I, how many values of x make f of x equal -3? All right, so it's asking you y equals -3. How many values of x make y is -3? So if you look, there's a y value of -3, so that's 1. There's actually another one somewhere in here that we can't actually find exactly because it didn't give us the number. That's 2. And then don't count the first one. Even though it says -3, it's an open circle, so we can't include. So how many values of x? 2 of them. One of them we could find, one of them you cannot find. And then finally, part J, what is the value of f of 2? So remember, f of 2, this is an x value that you're plugging in. So if you go to x equals 2, which is right there, that number occurs somewhere on this constant interval. And since on that constant interval, every value of y has to be the same, by looking at the point to the left and the point to the right, all of these y values have to be -1. So therefore, our y value has to be -1. So a lot of stuff on that problem, but all of those are properties of graphs and properties of functions graphs that we can deal with and know how to find. All right, and then last but not least, to wrap up section number 2 of this video, the idea of even and odd and neither. So functions whose graphs are symmetric about the y-axis are called even functions. So what I do, and this is kind of a picture right below it, this is kind of a picture of what an even function will look like. How I think of it is that if I were to take the y-axis and I cut this graph in half and you were to fold it, and I know it sounds weird, but imagine it like a piece of paper. If you fold that piece of paper and crease it at the y-axis, if the graphs end up overlaying each other, that is what's considered an even function. All right, a little bit trickier is an odd function. So functions whose graphs are symmetric about the origin are called odd functions. So what I do instead is that when you want to see if an odd function is existing, let's see, I kind of do this two ways, and this is kind of just the way that I do it. If you can divide, let me make sure I get my line correct here. I'm trying to think of how I want to draw. I don't want to cover the graph up, so give me 1 second to think about how I want to draw this. Oh, let's see. All right, so I'm going to do it this way. I think maybe goes in. So we're actually going to fold two ways. You have your y-axis. So obviously this is not an even function because if you fold this direction first, it's not going to overlay. But what you have to also do is you need to fold in the other direction as well. So you're going to fold from left to right, so fold vertically, and you're kind of folding it into a forts. Then you will fold again this direction. If those end up in the same spot, that is considered an odd function. Now usually what you can look at is that if you focus here on the origin, if you kind of see a mirror image in opposite quadrants here, that's another way that you can tell that they are odd. It's kind of preference here. I've seen it taught both ways, but I like the folding the paper method. Even though we're not literally folding paper, it kind of lets you visualize the idea. So what I did here is I picked out three graphs. One of them is even, one of them is odd, and one of them is neither, which means it's just not odd or even, which happens a lot. Can you find which one is which? So let's start with even. Which of these graphs is if you folded directly along the y-axis, so you fold the piece of paper one time, would be the exact same graph? Well, that is number 10. This is an example of an even function. If you fold it about this y-axis, like a piece of paper, you will have the same graph on both sides. All right, which one's odd? Well, the only other one that has any kind of symmetry to it would be number 9. This would be an example of an odd function. If you fold the piece of paper this way and then this way and you fold it into forts, your two graphs will overlay each other. And then looking at number 8, there is no kind of symmetry anywhere there. You can try your best, but that is an example. Even though it is a function, it's just not even or odd, and that's fine. You won't always have even and odd on every function you do. But that ends section 3.2, so that is the properties of functions graphs. So now we're going to move into the last section of this video, which is section 3.3, and that is the graphs of basic functions and piecewise functions. So there's two main concepts in this last section. Obviously, the graphs of basic functions, that part you're probably going to catch on to very quickly. The part that most students struggle with in this section that we're going to do at the very end is called piecewise functions. So make sure you pay attention when we get to that part of the section. All right, so let's just do here's the basic functions, and these will probably go pretty quick, but I still want to practice them with you on this video. Just making sure you remember how to draw a basic x squared graph. So pick out some x values that you think would help. And I'm going to try to be as symmetric as possible here. I'm going to do -2 for my x, -1, 0, 1, and 2. And I'm going to plug all 5 of those x values into my function to get the function value or the y value. So if I square -2, I get 4. If I square -1, I get 1. If you square 0, you get 0. If you square 1, you get 1. And if you square 2, you get 4. And what you have done here, and I'm going to write them all out for you, is you have just developed ordered pairs to plot this function. I know it's the same thing as like it's plotting points, and it's the most basic way to graph these, but I just want to make sure everybody sees where these graphs are coming from. So plot these points. -2, 4 is way up here. -1, 1 is here. 0, 0, 1, 1, and 2, 4. And as some of y'all probably remember from a previous section, but if not, when you draw an x squared graph from left to right, it forms this U shape, which is also known as a parabola. So that is why the basic function of x squared draws a parabola. So make sure you note that one. It comes back a lot later. One that we have not done is an absolute value function. So we haven't graphed any of these, even though I'm sure some of y'all remember what they look like. So can we sketch a basic graph of the absolute value of x? I'm actually going to use the exact same 5 x values. I'm going to do -2, -1, 0, 1, and 2. And I'm going to plug all 5 of those x values into the absolute value function. Now remember, all an absolute value function does is tell you to change it to a positive. So all of these numbers, you just change them to their positives. -2 becomes 2, -1 becomes 1, 0 stays as 0, and then 1 and 2 also don't change. So that makes you, once again, you have created 5 points that you can plot. -2, 2, -1, 1, 0, 0, 1, 1, and 2, 2. If you plot those points, so -2, 2 is here, -1, 1, 0, 0, 1, 1, and 2, 2. And maybe some of y'all remember, when you draw absolute value graphs, this is also known, and my graph's horrible, just kind of deal with it, you will draw a V shape. So absolute values always have a basic V shape that points and goes towards the origin. Kind of like the parabola was a nice smooth U. Absolute values are these little pointy V's you got to be able to draw. So very good. All right, what about a square root graph? This one may be the least popular of the 3. So you notice that I didn't put as many x value blanks this time because you need to be particular about what you pick. Don't just pick any x values, pick numbers that square roots are easy to find, such as 0, 1, 4, and 9. If I plug these 4 x values into a square root, it gives me better numbers to work with. So for example, the square root of 0 is 0, square root of 1 is 1, the square root of 4 is 2, the square root of 9 is 3. So that means I can form the 4 points of 0, 0, 1, 1, 4, 2, and 9, 3. So let's plot those. 0, 0 is the origin, then 1, 1, and then way out here at 4, 2, you'll notice the graph starts flattening really quick, and then way out here at 9, 3. If I play connect the dots, it's kind of like a graph that starts to increase really quick, and then it increases very, very slowly as you go to the right. So if that's a graph you haven't seen before, we're going to see it a little bit more in the next video, but that is the basic sketch of a square root of x graph. All right, so now we have to actually look at what happens when you restrict the domain. So what if I wanted you to draw that same x squared graph, but I want you to only graph it between -3 and 1, and notice the inequalities. So what I'm going to do is I'm going to start at -3. So we're going to go -3, -2, -1, 0, and 1. That's the interval they gave me. I'm going to plug all 5 of these x values into this function. So we're going to square them all. -3 squared is 9, -2 squared is 4, -1 squared is 1, 0 squared is 0, and 1 squared is 1. And you have 5 points here. -3, 9, -2, 4, -1, 1, 0, 0, and 1, 1. Now notice that there is not an equal sign on that inequality next to the 3. So when I go to the point -3, 9, which is not even on my graph, so I'll do my best here. Let's say -3, 9 is way up here. So -3, 9 is going to actually be an open circle because there's not an equal sign. -2, 4 is fine, so we can plot that point. -1, 1. 0, 0, and then since there is an equal sign on the last part of the interval, the last number 1, 1, we can put a closed circle. So since we're only graphing this between -3 and 1 on the graph, once again I apologize for the bad picture, you have to actually start and stop at those particular points. Versus the last few graphs we just put arrows on the end, this one you have to be a little bit more particular about. But that is a rough sketch of x squared on the interval from -3 to 1. All right, so now we get into, so that's kind of the basic part. I told you that part would go very simple. Now we get into the piecewise function part, so make sure you pay attention here. A piecewise function is a function that is defined over more than one interval. So you have to pay attention to not only the piece of the function you're working with, but which function you should use based on the interval or the domain that it's restricted on. So as you can see in this first one, it is defined as being 1 if x is less than 2. So anytime x is less than 2, you have to let it be 1. And if x is greater than or equal to 2, then you have to let the answer be -3. So look at our three choices here. On part A, it says find f of -2. Well, which one of these does it fall into? -2 is less than 2, so therefore it falls into the first category, so I know that my answer is 1. If I do 0, 0 is also less than 2. So since 0 is less than 2, it falls into the first category, and you get an answer of 1 again. But when you look at f of 3, 3 is bigger than or equal to 2, so it falls into the second category, so I can say that my answer is -3. So on piecewise functions, you have to make sure that you're evaluating your function based on the interval. You can't just pick whichever one you want to. So you have to pay attention to your inequalities here. So we're going to do that for the rest of this video. All right, so what about one where you actually have to plug numbers in? This one's got 3 pieces. This one says f of x is going to equal x squared if x is less than 0. So if x is small, or x is a negative number, you use x squared. If x is equal to 0, you say the answer is 4. And if x is greater than 0, you have to evaluate the square root of x. So let's look at all of these. On the first one, it says find f of -3. Well, if you look at your 3 parameters, -3 falls into the first one because -3 is less than 0. So I'm going to take that -3, and you have to plug it into the x squared function. So I'm going to square the -3, which gives me an answer of 9. For part B, it says f of 0. Well, since 0 is part of the second equation, and this piecewise function says if x is 0, which ours is, your answer has to be 4. Okay, well, you're done. That means it's telling us that you have to let the answer be 4. For f of 9 is obviously bigger than 0, so that's the third parameter, which means you have to plug the 9 into the square root function. So I would take the square root of 9, which is equal to 3. Once again, not only must you pay attention to which interval it falls into, you have to that's because you have to plug your number into the right function. If you had plugged, let's say, the -3 into the last one, you would have got the wrong answer. Or if I plugged 9 into the first one, that would be the wrong answer. So you have to pay attention on these piecewise functions. So what about graphing them? So what if you're asked to sketch the following piecewise defined function, where it says f of x is going to be 2 if x is less than 1, and -3 if x is greater than or equal to 1. Now, there's a bunch of ways teachers teach this. I'm going to do this probably the most basic way possible because I think it makes the most sense. I'm going to simply make myself as many t-charts as there are functions. So in this case, I've got my first equation and my second equation. So I'm going to work on these individually. Notice that the first one says that x must be less than 1, and the second one says that x must be greater than or equal to 1. Now, even though there's not an equal sign on both of these, what you're going to see me do here is that when I graph piecewise functions, I'm going to test that number on both. But what I am going to do, excuse me, is I'm going to put a little star next to the first one because I know that it doesn't exist, and we will end up putting an open circle on that part of the graph. Now, equation number 1 says I need numbers less than 1, so I'll pick a few extra. How about 0 and -1? And for equation number 2, it says x has to be bigger than 1, so why don't we pick 2 and 3? Now the other good thing is that we're not plugging numbers in because it says that for equation number 1, for every number less than 1, the answer is going to always be 2. And that's even going to include the one I have a star next to. So when I plot these points, when I go to the point 1, 2, I'm actually going to put an open circle because it doesn't actually exist there. But the rest of these points, the 0, 2, and the negative 1, 2, if I actually plot those, you'll notice that this ends up drawing a horizontal line that goes off to the left. On the second equation, it says all of your answers that are for x is greater than or equal to 1 have to be negative 3. Now there is an equal sign on this inequality, so all these points are going to be fine. You've got 1, negative 3 down here, and 2, negative 3, and 3, negative 3, and then you shoot off to the right, and that forms a horizontal line going off to the right direction. Now, why was it so important to note about those? So that's your answer. So first off, that's the answer for your homework. You're done with the problem. But why is it so important to note those open circles? Because if you remember, the vertical line test says that if you draw a vertical line anywhere, it cannot cross more than once. So if you had done 2 closed circles there, it would have failed the vertical line test. So you have to make sure you note which one will be an open circle and which one will be a closed circle. All right, so let's do one with actual numbers here. So what if f of x is 2x minus 1 for x is less than or equal to 0, and x plus 2 for x is greater than 0? All right, so I'm going to do my t-charts again. So we've got equation number 1 and equation number 2. So let me make 2 t-charts here. So xy and xy. One for equation 1 and one for equation 2. First thing I look for is what's the number that both of them change at. Well, you can see the 0 is defined in our interval. So while I am going to put 0 on both of these, notice that the equal sign is on the first equation. So I'm going to put a little star next to the second one to remind me to put an open circle on that. Equation number 1 says to pick numbers that are less than 0. So how about negative 1 and negative 2? For equation number 2, pick some numbers bigger than 0, so how about 1 and 2? Starting with equation 1, I'm going to take those 3 numbers that I have picked out and I'm going to plug them all into the 2x minus 1. Either do it on scratch paper. If you need to use your calculator, that's fine. I'm going to do them out loud to save a little time because this video is already getting kind of long. If you plug 0 in, 2 times 0 is 0, and 0 minus 1 is negative 1. If you plug negative 1 in, 2 times negative 1 is negative 2. Negative 2 minus 1 is negative 3. And finally, if you plug negative 2 in, you should get negative 5. So let's plot those 3 points. 0, negative 1, negative 1, negative 3, and my chart's a little off, but we'll make sure. Negative 2, negative 5 is somewhere down here, but it draws a line going in the downward left direction. So good. All right, so now I'm going to take the 0, the 1, and the 2 and plug them into the second equation. 0 plus 2 is 2, 1 plus 2 is 3, 2 plus 2 is 4. Now the 0, 2, you have to put an open circle on. That way it passes the vertical line test. Then you have the point 1, 3, and you have the point 2, 4. This one goes off in the opposite direction. So that is a sketch of this piecewise function. It passes the vertical line test because I made sure that I put the open circle and the closed circle on the correct spots. All right, and last but not least, and this is probably the worst problem, which is why I saved it for last. If I give you the graph of a piecewise function, can you actually write this function yourself? All right, so when you get to your homework, what you're going to see pop up here is you're going to see the little squiggle braces. You're going to have 4 boxes, I believe, if I remember right when I wrote this homework. You have to do both functions, and then you have to put their parameters in boxes as well. So we're going to practice like this is a homework problem. We're going to fill in all 4 of these boxes. Starting with the first one. Let's start with this line that's going at a slant. We need to find the equation of that line. So if you notice, it looks very similar back to chapter 2 like the form y equals mx plus b. So if you look at that graph, can you tell two things? What's its slope and what's its y-intercept? Well, I noticed right away that it crosses the y-axis at 0. So I know that my b value is going to be 0. And then remember, your slope is rise over run. So if I start at the far left point and I ask myself, how far did it go up? 1, 2, 3, 4, 5, 6. And then how far to the right did it go? 1, 2, 3, 4, 5, 6. So if your rise is 6 and your run is 6, 6 divided by 6 is 1, and you get a 1 for your slope. That means that you have just an x. One thing I left off here, you'll have f of x equals. So that takes care of the y. So you don't need to put y equals x. The only thing you have to put is the part on the other side of the equal sign. So I would put x. Now what is the interval? It has an interval that starts at -4 and ends at 2. So if I were to write that, I would write that as the interval from -4 to 2 because there's no arrow, so you have to define both endpoints of this function, and you're halfway done. On the second graph, that's this horizontal line. Now the good thing with horizontal lines is that we talked about before that means that is the form y equals a number. So if you look at that horizontal line, what is the y value on all of those? Well, they all have a y value of 3. So that means that the 3 is the part that I want to put on there. And then what would its interval be? Well, since it goes to the right forever, I could define this as for every x value that is greater than 2. Notice that I did not do greater than or equal because there is an open dot on the left-hand side of that horizontal line. So therefore, for every value x is greater than 2, the y value will always be 3 and form a horizontal line. We don't do a lot like that because those are a little bit tricky, but I did put a couple on your homework so you can practice writing your own piecewise functions. And after that long video, this ends sections 3.1 through 3.3. So once again, this is the start of your final exam material. In the next video, we will be doing the next 3 sections of chapter 3, which are 3.4, 3.5, and 3.6, and we'll get into some more about the graphing of these functions. So see you in the next video.